Imagine standing in a room so hot, so dense, that light itself cannot move, not because it's blocked, but because it's trapped. Every photon, every particle of light is constantly colliding, scattering, bouncing off a sea of charged particles like a pinball in an infinite machine. You can't see anything, not because it's dark, but because it's too bright, too chaotic, too full. This isn't a metaphor. This was the universe. For nearly 400,000 years after the Big Bang, the cosmos was a blinding, opaque fog. A seething plasma of protons, electrons, and light, all locked in an endless dance of collision and chaos. And then it stopped, not with a bang, not with a whimper, but with a sigh, a cooling, a letting go. As the universe expanded, it cooled. Space stretched, and with it, the energy of everything inside dropped. Temperatures fell from trillions of degrees to just a few thousand. And at that precise, fragile moment, when the cosmos was about 380,000 years old, something miraculous happened. Electrons, once too energetic to settle, finally slowed enough to be captured by protons. Hydrogen atoms formed. Helium followed. Neutral atoms, stable, quiet, transparent, began to appear. And in that instant, light was set free. For the first time in cosmic history, photons could travel unimpeded. No more collisions, no more scattering. The fog lifted, the universe became clear. And the light that had been trapped since the beginning, the afterglow of creation itself, rushed outward in all directions, carrying with it a snapshot of the infant cosmos. We still see it today. Not with our eyes, but with radio telescopes and satellite dishes pointed at the void. It comes to us as microwaves now, stretched by the expansion of space into a faint, cold hum just 2.7 degrees above absolute zero. This is the cosmic microwave background, the oldest light in existence. It's the final photograph of the hot, dense universe and the first moment of true darkness. Because once that light escaped, there was nothing else to shine. No stars, no galaxies, no suns. Just hydrogen, helium, and the fading echo of the Big Bang drifting through an ever-cooling void. The universe had gone from blinding brilliance to absolute silence, not because it died, but because it was waiting. Waiting for gravity to gather the scattered atoms, waiting for time to weave structure from chaos, waiting for the first spark. This is where our story truly begins, not at the explosion, but at the quiet that followed. The moment the lights went out and the long night began. For the next 100 million years, perhaps longer, the cosmos would know no light of its own, no fire, no color, no warmth from distant suns. Only the cold, expanding dark, punctuated by the ghostly whisper of that ancient radiation redshifted into oblivion. Astronomers call this era the Cosmic Dark Ages. Not because it's evil or empty, but because it is unseen. No telescope, until very recently, could pierce it. It is the universe's lost chapter, hidden between the last light of the Big Bang and the first flame of a star. And yet, within that darkness, something was stirring. Tiny imperfections, ripples no larger than a fraction of a degree in the cosmic microwave. Background were already planted in the fabric of space. These were not flaws, but blueprints. Seeds of future galaxies, clusters and stars, imprinted by quantum fluctuations, stretched to cosmic scales during inflation. That mysterious burst of expansion in the universe's first heartbeat. Invisible to any observer at the time, these slight overdensities held the promise of structure. Gravity, patient and relentless, would begin to pull matter toward them, ever so slowly, like water gathering in the hollows of a vast invisible landscape. But for now, there was only stillness. A universe adrift in its own infancy, cradled in darkness, dreaming of light. This silence is not emptiness. It is potential. It is the pause before the symphony. And in that pause, the stage was set for the most transformative event since the Big Bang itself, the birth of the first stars. We cannot see them directly, not yet. But we can feel their legacy in every atom of our bodies, in the iron in our blood, the calcium in our bones, the oxygen we breathe. All of it forged in stellar furnaces that did not exist until the Dark Ages ended. So how did it happen? How did fire rise from nothing? How did the first lights pierce the eternal night? To answer that, we must step deeper into the void, into the great dimming, where atoms drifted alone and time itself seemed to hold its breath. Picture this: you're floating in space, not near any star, not near any planet, just you and the void. But it's not the star-speckled blackness we know from Hubble images. There are no constellations, no Milky Way arching overhead. No distant galaxies glowing like embers. Just nothing. Pure, unbroken darkness in every direction. Not even the faintest glimmer. That's not science fiction. That was reality for 100 million years. This is the heart of the cosmic Dark Ages. Not a time of monsters or myths, but of profound, absolute stillness. After the last flash of the Big Bang faded into microwaves, the universe entered an era unlike any other, a time with no sources of light at all. No stars had yet formed. No black holes were feeding. No nebulae were glowing. The cosmos was filled only with neutral gas, mostly hydrogen, a little helium, and the ever-cooling echo of creation drifting silently through the expanding dark. It's hard for us to imagine. We live in a universe saturated with light. Streetlights, phone screens, the sun, the moon, even the air around us scatters photons. But back then, if you could somehow survive the cold and vacuum, you would see nothing. Not even your own hand in front of your face. Because there was no light to reflect off it. The universe wasn't just dark, it was optically dead. And yet, it wasn't empty, far from it. Think of the early cosmos as a vast invisible ocean. On the surface, calm and featureless. But beneath, currents were beginning to stir. Those tiny ripples we saw in the cosmic microwave background, the slight variations in density, were now the quiet architects of the future. In regions just a hair denser than average, gravity began its patient work. It pulled nearby atoms inward, ever so slowly, not with violence, but with inevitability. Like dust gathering in the corners of an abandoned room, matter started to clump. But here's the catch. In a universe filled only with neutral hydrogen and helium, there's no efficient way to cool down. Cooling is essential for star formation. When a cloud of gas collapses under gravity, it heats up, just like a bicycle pump gets warm when you compress air. If that heat can't escape, the pressure builds and collapse halts. Stars can't form unless the gas can shed its energy and keep shrinking. Today, that cooling happens thanks to heavy elements. Carbon, oxygen, silicon radiating heat away as infrared light. But in the Dark Ages, those elements didn't exist yet. The universe was chemically pure, pristine. Only hydrogen and helium atoms too simple to radiate efficiently. So how did the first stars ever ignite? The answer lies in a fragile, almost accidental molecule, molecular hydrogen. In the coldest, densest pockets of collapsing gas, two hydrogen atoms could briefly pair up to form H2. Not stable like water or oxygen, but enough to act as a tiny radiator. Molecular hydrogen could vibrate, rotate, and emit faint infrared photons, just enough to let the cloud cool by a few tens of degrees. It wasn't much, but in the silent economy of the early universe, it was everything. Like a single candle in a frozen cathedral, it provided the bare minimum needed to tip the balance. Still, the process was agonizingly slow. Gravity worked in whispers, not shouts. It took tens of millions of years for the first clumps to grow massive enough, thousands of times the mass of our sun, to begin collapsing in earnest. And even then, conditions were unlike anything we see today. No planets orbited these future stars, no asteroid belts, no companions. Just solitary, monstrous clouds of pure gas, collapsing in perfect isolation, in total darkness. This was a universe without color, without sound, without landmarks. Time stretched like taffy. Generations of hypothetical observers would have lived and died without ever seeing a single point of light in the sky. The cosmos was holding its breath. And yet, something extraordinary was happening in the shadows. In the deepest wells of gravity, densities climbed, temperatures rose, pressures mounted, and deep within those collapsing clouds, conditions began to approach the threshold of nuclear fire. But before we witness that first spark, we must understand what made it possible, not just physics, but the hidden architecture of the void itself. Because the Dark Ages weren't just empty space waiting to be filled. They were woven with invisible threads, ghostly filaments of dark matter that guided the flow of gas-like rivers in the night. Without those unseen currents, there would be no stars, no galaxies, no us. So let's pull back the veil, not with light, but with gravity's silent map, and see how the universe built its first cradles in the dark. If you could see the universe during the Dark Ages, not with light, but with some impossible sense that revealed gravity itself, you wouldn't see emptiness. You'd see a web. A vast, intricate, three-dimensional tapestry stretching across billions of light years, made not of stars or gas, but of something far stranger, dark matter. We can't see it. It doesn't glow, absorb, or reflect light. It doesn't interact with atoms at all, except through gravity. And yet, it makes up about 85% of all matter in the cosmos. It's the hidden skeleton upon which the visible universe is built. And during the Dark Ages, it was already hard at work. Here's how it began. In the first fraction of a second after the Big Bang, during a phase called cosmic inflation, the universe expanded faster than the speed of light. Not because things moved through space, but because space itself stretched. In that violent expansion, quantum fluctuations, tiny random jitters in energy at the subatomic scale, were blown up to cosmic proportions. These became the seeds, slight variations in density, imprinted across the newborn universe. When matter finally formed, both normal and dark, it responded to those seeds. But dark matter had a crucial advantage. It didn't interact with light. While normal matter was still trapped in the hot plasma, bouncing around like popcorn in a kettle, dark matter was already free to move. It began collapsing under its own gravity long before atoms even existed. By the time the universe became transparent, when the cosmic microwave background was released, dark matter had already formed a cosmic scaffolding. Clumps, filaments, and halos, invisible but massive, dotted the void. These weren't smooth spheres. They were lumpy, dynamic structures, constantly merging and growing, like roots spreading through soil. And when neutral hydrogen finally filled the cosmos, it didn't drift aimlessly. It flowed, guided by the gravitational valleys carved by dark matter. Think of it like rain falling on a mountain range. The water doesn't pool evenly. It gathers in gullies, streams, and basins shaped by the land beneath. In the same way, gas poured into the gravitational wells of dark matter halos, pooling in their centers like liquid in invisible bowls. The smallest of these halos, each only about 1,000,000 times the mass of our Sun, became the nurseries for the first stars. Not because they were special, but because they were the first to reach a critical threshold. In larger structures, gas would take longer to cool and collapse. But in these modest halos, molecular hydrogen could do its fragile work just well enough to allow contraction to continue. This is where the story shifts from passive waiting to active creation. The Dark Ages weren't a blank canvas. They were a blueprint, slowly coming to life. Every ripple in the microwave sky corresponded to a future cluster of galaxies. Every cold spot hinted at a void. Every warm patch marked a cradle of stars yet unborn. And the most astonishing part, we've measured those ripples. With satellites like COB, WMAP, and Planck, we've mapped the infant universe in exquisite detail. We can see the seeds. We can calculate how they grew. We can simulate on supercomputers how gas flowed into dark matter halos, how clouds collapsed, how temperatures rose. One such simulation, run by teams at institutions like MIT, Harvard, and the Max Planck Institute, shows a single dark matter halo, just a few 100,000 light-years across, pulling in hydrogen from all directions. Over millions of years, the gas spirals inward, forming a dense, turbulent core. No rotation like today's stars. No disks, just a chaotic, churning ball of primordial gas, growing hotter and denser by the day. At the center, densities climb to levels we can barely fathom, millions of atoms per cubic centimeter, compared to the near-perfect vacuum of interstellar space today. Temperatures soar past 10,000 degrees, then 20,000, then 100,000. Still no light. Not yet, because light requires fusion. And fusion requires even more extreme conditions. But the stage is set. The trap is sprung. Gravity has done its work. The gas has no escape. And deep in the heart of that dark cloud, something unprecedented is about to happen. Atoms will be forced so close together that they overcome their natural repulsion and fuse. For the first time since the Big Bang, new energy will be born. Not from expansion, not from cooling, but from creation itself. This moment, when the first atomic nuclei merge and release light, marks the end of the cosmic dark ages. But it doesn't happen in a flash. It begins in silence, in pressure, in heat, and then finally in fire. To understand that fire, we must meet the stars that lit it. Stars unlike any that exist today. Stars so massive, so pure, so short-lived, they seem more myth than reality. And yet, they were real. They lived. They died. And in their death, they gave us everything. But first, let's stand at the threshold of that first ignition and witness the birth of light in a universe that had forgotten what it was. Deep in the heart of a collapsing cloud of pure hydrogen and helium, no metals, no dust, no planets, no companions. A pressure builds that has not existed since the first 3 minutes of the universe. Gravity, relentless and patient, has squeezed this primordial gas for tens of millions of years. Now, at the core, atoms are packed so tightly that they move at thousands of kilometers per second. Collisions become violent. Electrons are stripped away. The gas turns into plasma once more, not the chaotic soup of the early universe, but a focused, seething furnace hidden in perfect darkness. And then it happens. Two protons, hydrogen nuclei, smash together with such force that they overcome their mutual repulsion. For a fleeting instant, they fuse. A tiny bit of mass vanishes, converted into pure energy as Einstein's equation demands. A gamma-ray photon is born. Then another, and another. Nuclear fusion has ignited. But this is not the gentle, steady burn of our sun. This is something far more extreme. The first stars, called population 3 stars by astronomers, were not like the stars we see tonight. They were titans. Born in isolation, fed by pristine gas, and unburdened by the cooling effects of heavy elements, they grew to staggering sizes. Simulations suggest most were between 30 and 300 times the mass of our sun. Some may have reached 1,000 solar masses, monsters that would dwarf even the brightest stars in the Milky Way. Why so massive? Because without heavy elements, gas couldn't fragment easily. Today, when a molecular cloud collapses, it breaks into dozens or hundreds of smaller clumps, each becoming a star. But in the Dark Ages, the gas stayed hot and smooth. It collapsed as one enormous unit. Like a single drop of water falling instead of a mist, the entire cloud funneled its mass into one central object. And when that object lit up, it did so with terrifying brilliance. Imagine a star so luminous that, if placed at the distance of our nearest stellar neighbor, Proxima Centauri, it would outshine the full moon in our night sky by a factor of 10. Its surface temperature? Over 100,000 degrees, 5 times hotter than the sun. Its ultraviolet radiation, so intense it could ionize hydrogen atoms light years away. Yet no one saw it. There were no eyes, no planets, no life. Just this solitary beacon flaring to life in an ocean of black. Its light streamed outward in all directions, the first new photons since the Big Bang's afterglow. But space was still filled with neutral hydrogen, a fog that absorbed ultraviolet light like a sponge. So the star's brilliance didn't travel far. It was trapped, scattered, reabsorbed within a few light years. To any hypothetical observer nearby, the sky would still appear utterly dark. But inside the star, a maelstrom of creation. In its core, hydrogen fused into helium at a furious rate. Because of its enormous mass, gravity pressed down with crushing force, driving temperatures to over 10 million degrees. The star burned its fuel not over billions of years like our sun, but in a few million, perhaps even just a few 100,000. It lived fast, it burned bright, and it was already dying the moment it was born. These stars had no planetary systems, no asteroid belts, no chance for life. They existed only to transform the universe. Their intense radiation began to push back against the surrounding gas, creating bubbles of ionized hydrogen, tiny pockets of transparency in the cosmic fog. Their stellar winds, though weak compared to later stars, started stirring the interstellar medium. And deep in their cores, something even more profound was happening, the forging of new elements. For the first time since the Big Bang, atoms heavier than helium were being made. Not in large quantities. Population 3 stars fused hydrogen to helium, and in their final days, helium to carbon and oxygen. But that was enough. When they died, and they died quickly, they scattered these first heavy elements into space. And with that act, they changed everything. But their deaths were not gentle. Stars above a certain mass, about 25 times that of our Sun, cannot end as white dwarfs. They collapse catastrophically. And for the most massive among them, the end came not with a supernova as we know it, but with something even more violent, a pair instability supernova. Here's how it works. In the core of an extremely massive star, temperatures become so high that gamma ray photons spontaneously transform into electron-positron pairs. This robs the core of radiation pressure, the very force holding the star up against gravity. Suddenly, the star implodes. Then, in a runaway thermonuclear explosion, it blows itself completely apart. No black hole left behind, just an expanding cloud of newly forged elements: carbon, oxygen, silicon, iron. In some cases, if the star was truly enormous, over 250 solar masses, it may have collapsed directly into a black hole without any explosion at all, swallowing its enriched material forever. But even then, its intense radiation during life would have altered its surroundings. Either way, the message was clear. The age of purity was over. The universe had tasted complexity, and it would never go back. These first stars were not just lights in the dark. They were alchemists. They turned the simple into the rich. They took a cosmos made of only 2 ingredients and began writing the recipe for everything that would follow: rock, water, DNA, consciousness. But their legacy wasn't just chemical, it was cosmic. Their ultraviolet light began the slow, epochal process of reionization, ripping electrons from neutral hydrogen atoms across the universe. One star alone couldn't do it. But as more formed, their combined radiation grew stronger. Bubbles of ionized gas merged. The fog began to lift. The Dark Ages were ending, not with a single dawn, but with 1,000 dawns scattered across the void. And from the ashes of these first giants, a new generation of stars would rise, smaller, longer-lived, and rich with the elements of creation. Stars that could host planets, stars that could nurture life. But before we meet them, we must witness the true miracle of the first stars. Not just that they existed, but that they changed the rules of existence itself. They turned a silent, simple universe into one capable of wonder. And that transformation began not with a whisper, but with fire. When the first stars died, they didn't just vanish. They exploded, not merely in space, but into time. Their deaths sent ripples forward through the eons, shaping the chemistry of galaxies, the formation of planets, and, ultimately, the very possibility of life. Because before those stars, the universe had only hydrogen, helium, and trace lithium elements, forged in the first minutes after the Big Bang. Everything else, the calcium in your bones, the iron in your blood, the oxygen you breathe, was made later, inside stars. And the very first batch of those metals, as astronomers call all elements heavier than helium, came from the corpses of population 3 stars. This was cosmic alchemy on a scale no human ever dreamed of. Not turning lead into gold, but turning nothing into everything. Consider carbon, the backbone of organic chemistry. In the cores of massive first stars, once hydrogen was exhausted, helium began fusing. 3 helium nuclei under immense heat and pressure collided to form carbon. It's a delicate process, requiring just the right conditions. A resonance in nuclear physics so precise that if it was slightly different, carbon might not exist at all. Yet in those ancient furnaces, it happened. Oxygen followed as carbon captured more helium. Then neon, magnesium, silicon. Each layer of fusion building heavier elements like an onion growing inward. But unlike later stars, which gently shed their outer layers over time, the first stars ended violently. In a pair instability supernova, a detonation so total it leaves no remnant. The entire star is vaporized. Every atom it ever forged is blasted into the surrounding void at thousands of kilometers per second. For a brief moment, a cloud of gas that was once pure hydrogen becomes sprinkled with stardust, carbon grains, oxygen molecules, iron nuclei seeds of future complexity. And this dust changed everything. Before metals, gas clouds couldn't cool efficiently. But now, even a tiny amount of carbon or oxygen acted like a radiator. These atoms could emit infrared light when excited, allowing gas to lose heat far more effectively than molecular hydrogen ever could. That meant clouds could fragment into smaller clumps. Instead of forming one monstrous star, a cloud could now birth dozens, some small enough to live for billions of years. This was the birth of population 2 stars. Older, metal-poor, but no longer pristine, and eventually population 1 stars like our Sun, rich in metals, stable, long-lived, and capable of hosting rocky planets. But the first enrichment was patchy. Not every region of space received the same dose. Some pockets remained pure for longer, others were seeded early. This uneven mixing explains why, even today, astronomers find ancient stars in the halo of our galaxy, with almost no metals. Fossils from the second generation of star formation, born from gas barely touched by the first supernovae. We've never seen a true population 3 star. They died too quickly, too long ago. But we hunt for their fingerprints. In 2014, astronomers studying a distant quasar found a gas cloud with no detectable metals, possibly a relic from before the first stars polluted the cosmos. In 2022, the James Webb Space Telescope spotted candidate galaxies so bright and so early that they may contain traces of population 3 light. These ancient stars didn't just make elements, they altered the physics of the universe. Their ultraviolet radiation began ionizing hydrogen, yes, but their supernovae did something equally vital. They stirred the interstellar medium. Shock waves from explosions compressed nearby gas, triggering new rounds of star formation. They created turbulence, mixed chemicals, and built pressure fronts that shaped the birthplaces of future stars. The universe went from static to dynamic, from passive to creative. And perhaps most profoundly, they enabled diversity. Before the first stars, every star that could form would have been massive and short-lived. After them, the stellar population exploded in variety. Red dwarfs burning for trillions of years, blue giants blazing for millions, white dwarfs cooling slowly into darkness. Planets became possible. Rocky worlds needing silicon and iron, gas giants needing carbon and oxygen to form icy cores. Water, H2O, could not exist without oxygen. DNA could not exist without carbon, nitrogen, phosphorus. You are literally made of recycled stardust from stars that lived and died before the Milky Way even existed. And it all began with those first solitary giants, burning in darkness, unseen, unknown, yet utterly essential. Their legacy isn't just in telescopes or simulations, it's in your breath, in your heartbeat, in the fact that you can look up at the night sky and wonder where you came from. But their work wasn't done when they died, because the light they emitted, though absorbed locally, began a much larger transformation. One that would take hundreds of millions of years to complete, but would ultimately clear the cosmic fog forever. That process, reionization, wasn't the work of 1 star or even 1,000. It was a collective awakening. And as more stars formed, as galaxies began to assemble, their combined light turned the universe from neutral to ionized, from dark to transparent. The dawn was coming. Not with a single sunrise, but with a slow, relentless brightening like embers catching across a vast forest floor. And when it finally broke, the universe would never be the same. For 100 million years, the universe had been wrapped in a soft, invisible shroud, a fog of neutral hydrogen that filled every corner of space. It wasn't thick like smoke, nor dark like soot. It was transparent to visible light, yes, but utterly opaque to the high-energy ultraviolet photons that stars produce. So when the first stars ignited, their most powerful light didn't travel far. It was swallowed almost instantly, absorbed by the very gas that had birthed them. The cosmos remained cloaked, silent, and dark to any outside observer. But stars are persistent, and as more of them formed, first in ones and twos, then in clusters, then in the first protogalaxies, their combined radiation began to push back. Imagine a single candle in a vast, damp cave. At first, it only lights a small circle around itself, but add another candle, and another. Soon the walls begin to glisten, patches of dry rock appear, then entire chambers glow. The moisture doesn't vanish. It's driven away molecule by molecule as heat and light break the bonds holding it in place. That's what ultraviolet light did to hydrogen. Each photon with enough energy could strike a neutral hydrogen atom and knock it electron-free, a process called photoionization. The atom became ionized, a lone proton and a free electron, no longer able to absorb that kind of light. And once ionized, the gas became transparent to ultraviolet radiation. The fog lifted, not all at once, but in expanding bubbles around the brightest sources. These bubbles grew. They merged. Over hundreds of millions of years, they stitched together into vast ionized regions. And eventually, they consumed the entire observable universe. This was the epoch of reionization, the grand finale of the cosmic dark ages. It didn't happen overnight. Evidence from the cosmic microwave background tells us it began around 250 million years after the Big Bang and wasn't complete until about 1 billion years in. That's a span longer than all of recorded human history compressed into a single cosmic chapter. And the sources? For decades, astronomers debated, were the first stars enough? Or did we need something more powerful? Like quasars, the blazing cores of galaxies powered by supermassive black holes. Now, thanks to the James Webb Space Telescope, the answer is becoming clear. The earliest galaxies, small, chaotic, but incredibly numerous, were likely the main drivers. They may not have been as bright as quasars, but there were so many of them, packed tightly in the dense early universe, that their collective glow was overwhelming. Think of it not as a few lighthouses, but as countless fireflies rising from a dark field, each faint, but together illuminating the night. One of Webb's most stunning discoveries is a galaxy called Jade's GSZ 13-0, seen as it was just 320 million years after the Big Bang. It's small, only about 1% the mass of the Milky Way, but it's forming stars at a furious rate. Galaxies like this, repeated thousands of times across the sky, could easily produce enough ultraviolet light to reionize the cosmos. But here's the twist. Reionization wasn't just about light. It was a feedback loop. As gas became ionized, it heated up, reaching temperatures of 10,000 degrees or more. Hot gas doesn't collapse easily. So in small, dark matter halos, star formation was actually suppressed. The very light that ended the Dark Ages also put a brake on the birth of future stars in the tiniest galaxies. This explains why we see so few ultra-faint dwarf galaxies today. They were quenched early by the heat of reionization. In larger halos, though, gravity was strong enough to hold onto the gas despite the heat. Those became the seeds of galaxies like our own. So reionization didn't just clear the fog, it sculpted the galaxy population we see today. And when it was finally complete, when the last pockets of neutral hydrogen were ionized, The universe became truly transparent. Light could travel unimpeded across billions of light years. The stage was set for the cosmos we know, a web of galaxies, glowing in visible light, radio waves, X-rays, every wavelength now free to tell its story. The Dark Ages were over, but their echo remained, not in light, but in a faint radio whisper hidden in the static between stations, a signal so subtle, so ancient, it might hold the final key to understanding how the first stars truly lived. And for decades, astronomers have been building strange antennas in remote deserts and quiet valleys, listening, waiting for that whisper to speak. Turn on an old analog radio. Tune it between stations. Hear that hiss, that crackle of white noise? Most of it is human-made interference, cell towers, satellites, microwave ovens. But buried deep within that static, quieter than a whisper, is a signal from the edge of time. Not from aliens, not from black holes, but from the hydrogen gas that filled the universe during the cosmic dark ages. This is the 21-centimeter line, the universe's oldest radio beacon. It comes from a quirk of quantum physics. A neutral hydrogen atom consists of a proton and an electron, each with a property called spin. Most of the time, their spins are opposite, which is a low-energy state. But occasionally, they flip to align. And when they do, the atom holds a tiny bit more energy. Then, after an average of 10 million years, the electron flips back, releasing that excess energy as a photon with a wavelength of exactly 21 centimeters, about the length of a standard ruler. That's radio light. And because hydrogen was everywhere during the Dark Ages, this signal was too faint, uniform, and omnipresent. But here's the magic. As the universe expanded, that 21-centimeter signal got stretched. The farther back in time the emission happened, the longer the wavelength we detect today. Hydrogen from 300 million years after the Big Bang reaches us, not at 21 centimeters, but at 2 or 3 meters deep in the FM radio band. So if we point a radio telescope at the right frequency, we can, in theory, see the distribution of hydrogen during the Dark Ages and the cosmic dawn, the era when the first stars began to shine. Not by seeing the stars themselves, but by seeing how their light changed the gas around them. When ultraviolet photons from the first stars hit neutral hydrogen, they didn't just ionize it, they also excited the atoms into that higher spin state. This created a subtle absorption or emission feature in the 21 centimeter signal, depending on the gas temperature. In some models, the signal should appear as a dipper shadow against the cosmic microwave background. In others, it might glow faintly. Either way, it's a direct probe of the invisible. For decades, this remained theoretical. The signal is incredibly weak, about 1,000 times fainter than the radio noise from our own galaxy. And Earth is a terrible place to listen. Human radio pollution drowns it out completely. Even in the quietest deserts, FM stations, aircraft, and satellites leak interference. But astronomers didn't give up. In remote corners of the world, they built strange instruments. In Western Australia, the Murchison Wide Field Array sprawls across the red outback, a grid of simple dipole antennas, no dishes, just metal rods pointed at the sky, listening for the hum of the infant universe. In South Africa, the Hydrogen Epoch of Reionization Array. HERA uses 350 closely packed dishes, all tuned to low frequencies, working together like a single giant ear. And in the future, there are plans to put antennas on the far side of the moon, where Earth's radio chatter can never reach. Then, in 2018, came a shock. A small team using an instrument called edges, just a single metal tray on legs in the Australian desert, reported a detection. They claim to have seen the 21 cm absorption signal from about 180 million years after the Big Bang, but the dip was twice as deep as predicted. To explain it, the hydrogen gas would have had to be much colder than expected, or the cosmic microwave background much warmer. One radical idea emerged. Maybe the gas was cooled by interactions with dark matter. If certain types of dark matter particles existed, light, slow-moving, and weakly interacting, they could have siphoned heat from the hydrogen, making it colder than standard physics allows. The result sent shockwaves through cosmology, but it also sparked intense skepticism. Other teams couldn't reproduce it. Some suggested the signal was contaminated by subtle instrumental effects or unmodeled galactic foregrounds. As of now, the edge's detection remains unconfirmed, tantalizing but not yet proven. That's the challenge of this science. We're not just looking for a signal. We're trying to hear a single note in a symphony of noise, played on an instrument we barely understand, from a time before time had landmarks. Yet the pursuit continues, because if we can detect this signal cleanly, we'll do something unprecedented: map the universe in 3 dimensions during the Dark Ages. Not just see when the first stars formed, but where. We could trace the growth of ionized bubbles, measure the temperature of primordial gas, test theories of dark matter, even probe physics beyond the standard model. This isn't just astronomy, it's archaeology of the void. And while radio telescopes listen from Earth, another kind of eye is scanning the heavens from orbit, peering not at radio waves, but at infrared light from the very first galaxies. An eye so sharp, so sensitive, it was built to see the impossible. Its name is James Webb. And what it has already revealed is rewriting our origin story. High above Earth, orbiting the Sun at a point 1.5 million kilometers away, floats a golden eye. It's not made of glass, but of beryllium light, strong and chilled to -223 degrees Celsius. Its mirror, 6.5 meters across, unfolds like a flower in the void. Its instruments peer not in visible light, but in infrared, the stretched reddened glow of the most distant objects in the universe. This is the James Webb Space Telescope, and it was built for one purpose: to see the first light. Before Webb, our view of the early universe was like trying to read a book with half the pages missing. The Hubble Space Telescope pushed the frontier back to about 600 million years after the Big Bang. But the era of the first stars and galaxies, the cosmic dawn, remained hidden, shrouded in redshift and dust. Hubble simply wasn't sensitive enough, and its mirror wasn't big enough to collect the faint, stretched photons from that time. Webb changed everything. Within months of its launch, it began delivering images that stunned astronomers. Galaxies where none should be. Bright, massive structures existing far earlier than our best models predicted. One object, GNZ1, once thought to be the earliest known galaxy, was suddenly joined by dozens of contenders, some seen when the universe was only 300 million years old. But Webb didn't just find galaxies. It found too many of them, and they were too bright. According to standard cosmology, structure should have grown slowly, small clumps merging over time into larger ones. The first galaxies should have been tiny, dim, and chaotic, yet Webb sees galaxies with a mass of billions of suns, forming stars at prodigious rates, already showing signs of maturity. Some appear to have disks. Others show clumps that might be star-forming regions. A few even hint at the presence of heavy elements, suggesting that star formation and death had already occurred multiple times. This isn't just surprising, it's potentially revolutionary. One possibility is that our models of dark matter need tweaking. If dark matter is slightly warmer, meaning its particles moved faster in the early universe, it could suppress small structures and allow larger ones to form earlier. Another idea is that the first stars were even more efficient at forming galaxies than we thought, or that black holes played a role sooner than expected. But there's another, more thrilling interpretation. Some of these galaxies might contain traces of population 3 stars. Webb can't see individual first stars. They're too faint, too distant. But if a galaxy is dominated by them, its light would have a distinct signature, extremely blue in the ultraviolet before redshift, with no absorption lines from metals. In 2023, a team analyzing Webb data from a galaxy called GNZ13 reported an unusual lack of metal lines and an excess of ionizing photons, consistent with a population of very massive metal-free stars. It's not proof, but it's a clue. Even more powerful is Webb's ability to study reionization in action. By analyzing the spectra of distant quasars and galaxies, astronomers can measure how much neutral hydrogen still existed along the line of sight. The results show that reionization was patchy. Some regions ionized early, others late, exactly as predicted by the bubble model. Webb is mapping the transition in real time, watching the fog lift across cosmic history. And then there are the surprises no one predicted. In one deep field, Webb detected an object so bright and so red that it defied classification. Was it a supermassive black hole already grown to millions of solar masses? A galaxy undergoing a burst of star formation unlike anything seen before? Or something entirely new? The debate continues. What's clear is this: the early universe was more active, more structured, and more luminous than we ever imagined. And Webb is just getting started. Future observations will target specific candidate galaxies with longer exposures, hunting for the chemical fingerprints of the first supernovae. It will peer into the hearts of early star clusters, measure stellar masses, and trace the flow of gas in and out of infant galaxies. Combined with radio data from 21 C-meters experiments and simulations running on the world's fastest supercomputers, Webb is helping us assemble the first coherent narrative of cosmic dawn. But even with all this power, there's a limit to what light can tell us. Because the true legacy of the Dark Ages isn't just in photons, it's in us. Every atom in your body, except hydrogen, was forged in stars that lived and died in the wake of that first fire. The oxygen you breathe, the iron in your blood, the calcium in your teeth, all were scattered across the cosmos by explosions that happened before Earth existed. You are not just in the universe, you are of it. And your story begins not with life on Earth, but with silence in the void. Which brings us to the final chapter. Not of cosmic history, but of human meaning. You are standing on a planet made of stardust, breathing air forged in ancient fires. Your thoughts shaped by a brain built from atoms that once drifted in total darkness. You exist because, for 100 million years, the universe chose to wait. It held its breath. It gathered its strength. It let gravity weave invisible threads across the void until the moment was right and the first star could be born. That star didn't know it was lighting the way for life. It didn't know its death would seed galaxies with the ingredients of planets, oceans, and DNA. It simply burned, fiercely, briefly, beautifully, and vanished. But in vanishing, it gave the cosmos a new language, the language of complexity. Before the Dark Ages, the universe spoke only in hydrogen and helium, simple, repetitive, pure. After them, it learned to speak in carbon, oxygen, iron, gold. It learned to build molecules, rocks, atmospheres, cells. It learned to wonder. And that wondering, that ache to understand where we came from, is what brought us here, to this moment, listening to a story written in light and silence. The cosmic dark ages were not a void to be feared. They were a necessary pause, a cosmic gestation. Just as a seed must lie in darkness before it sprouts, just as a thought must form in silence before it's spoken, the universe needed time to prepare its first act of creation beyond the Big Bang. Without that long night, there would be no dawn. Without that stillness, no symphony. And we are the symphony. Every time you look up at the stars, not the ones you see, but the ones you don't see, the ones that lived and died before galaxies formed, you are gazing into your own origin. You carry within you the ashes of monsters that burned hotter than anything imaginable in a time when the sky was truly black. You are the universe remembering itself. This isn't poetry, it's physics. Verified, tested, observed. When you feel small beneath the night sky, remember this: you are made of the rarest stuff in existence. Elements forged in the hearts of the first stars, scattered across billions of years, gathered by gravity into a planet, and arranged by chemistry into a being that can ask, "Why am I here?" That question is the universe's greatest miracle. And the Dark Ages remind us that meaning doesn't require light to exist. It can grow in silence. It can be born from absence. Sometimes the most profound transformations happen not in blaze, but in the quiet between. Today, as we build telescopes on Earth and in space, as we listen to radio whispers from the edge of time, we are not just studying the past. We are continuing the work of those first stars. We are turning darkness into knowledge, silence into story, mystery into meaning. We are the children of the Dark Ages. And our light, fragile, fleeting, but fiercely curious is the next chapter in a story that began with nothing and dared to become everything.